Okay, this next lesson is about simple harmonic motion with pendulums. Now, the equations of motion for simple harmonic for pendulums are actually derived from specific conditions, specifically small angles for which we can make approximation. So the equations aren't exactly absolute, but they make for a good approximation for small angles. Let's look at the free body diagram here of a pendulum that's oscillating back and forth at a small angle theta. Now, the free body diagram of this pendulum includes, if we want to break up the gravity component into two different directions, a component of gravity that's in the direction of the net force. So clearly the pendulum itself is not going to accelerate along the same line of motion as the length of the string. So it's accelerating perpendicular to that. It's accelerating tangent to its arc. Now, let's pretend we could look at this pendulum oscillating from underneath, and that's our I. Now, to us, if we have zero depth perception, this ball would look like something that just oscillates back and forth, assuming zero depth perception. And it's going to basically oscillate back and forth at a displacement of x to our I, which in this case would be equal to L times sine of theta. Now let's do some algebra and some approximation. So we know for a simple harmonic motion in spring, we can take Hooke's law, first of all, a restoration force of kx, and if we imagine that this is a spring system oscillating back and forth, then that is equal to m times a. But in this case, the driving force is going to be the tiny little blue component. I don't know if you can see, but this is one of the first of our many lies to come. For a small angle, those two component forces are approximately the same, where this, if I zoomed in, was mg sine theta. That's these two right here. Now, they're not exactly the same thing, but we can say approximately for a small theta, they are the same thing. So I'm going to say that they are the same thing, lie number one. And for small theta, we can also approximate, here we go, this component that we're calling x. I guess this applies to any theta. Sine of theta is opposite over hypotenuse, so that's just x over L. So I could say m times g times x over L is equal to negative kx. Now I've got an x on both sides, so that can go away. And then I have k is quantified by mg over L. And the other lie is that I forgot the negative sign. Oops, lie, it's gone. Now I know that in a simple harmonic oscillator, for my equation for angular frequency of a spring system, I have angular frequency is equal to the square root of k over m. Now I see those two variables here, k over m, or k and m, here they are. Now if I can get that same format, k over m square root, then I have the same sort of expression for angular frequency. So if I divide both sides by m, I get k divided by m is equal to g divided by L. So then if I take the square root of both sides, I should get omega. So I could also say that omega is equal to the square root of g over L. Isn't that lovely? Now I can substitute this value in to get expressions for period end frequency of a pendulum, because I know that omega is equal to 2 pi f by definition. So frequency is 1 over 2 pi times omega. In other words, 1 over 2 pi times the square root of g over L. So we're going to have this formula for frequency of a pendulum. So frequency of a pendulum is the square root, or 1 over square root of 2 pi g over L. And we also know that the period is the inverse of our frequency. So we're going to set that equal to 2 pi square root L over G. And those are our two equations for pendulum oscillation. Now it's very important to note that this only happens for very small angles. If you have any angle greater than, say, 15 degrees, it's completely wrong. There's no way that you can approximate those two to be equal once you get to a larger angle. So you won't end up using the same equation. You would not be able to apply it for what I don't consider small angles. It's only good for a small angle approximation.